So let's do the final part of the curve sketching. This is the one called oblique asymptotes. We've had horizontal asymptotes, we've had vertical asymptotes. Now we have oblique asymptotes. And we only deal with straight lines. So in other words, it's an asymptote with an equation of y equals mx plus c. They're neither horizontal nor vertical nor multiple of 90 degrees. Here's some graphs with oblique asymptotes. There we are, getting closer and closer to that line. Here it's approaching that line. It's in fact also approaching the y-axis, approaching another line, and also approaching the y-axis. Here we are. Here's an oblique axis and a vertical axis. Here's an oblique axis. I've got to think about abscesses. I think right at a vertical axis, and then here's one with two vertical axes. We can also have curved asymptotes, though we don't deal with them in this course. That'll only be in tertiary courses. Now, so we must say oblique asymptotes occur when a function in x approaches another function in x as x tends to infinity. And in this course, it's just a linear function in x that it approaches. First, a note, a deviation from the usual limit calculations. Usually we would say, for example, limit of 2x plus 1 as x tends to infinity does not exist. Or, in tertiary, limit of 2x plus 1 as x tends to infinity is infinity. But when we go to curves, we change that because we need to determine the behavior of the curve along the way. So in fact, the limit of a polynomial as x tends to infinity is the polynomial. So therefore, that original one where we're talking about does not exist or equal to infinity, here we say the limit of 2x plus 1 as x tends to infinity is 2x plus 1. And here's a picture of it. There, approaching 2x plus 1 as x tends to infinity. So let's have a look at a function. F of x equals x plus 1 over x. Now notice that it has two parts. It has 1 over x, which in fact tends to 0 as x tends to infinity, and then it has x, which by the previous screen tends to x as x tends to infinity. So therefore the graph of 1 over x plus 1 over x, which is asymptotic to x equals 0, there's common denominator, or we could even pick it up from there, asymptotic to the line x equals 0, the y-axis, but it's also asymptotic to the line y equals x. There we are, there's the curve. If you want to see whether a curve has oblique asymptotes or not by looking at its equation, all you have to check is whether the numerator is of a greater degree than the denominator. This one here, for example, if we find a common denominator, you'll see degree 2, degree 1. Degree 2 in the numerator, degree 1 in the denominator. And immediately that tells us that this must have an oblique asymptote. So, the limit of f of x as x tends to infinity is mx plus c. That's the sort of oblique asymptote we're dealing with. Or x tends to negative infinity. Now let's have a brief look at what you'll probably do in tertiary education. You can do this by a formula. First of all, we start by saying the limit as x tends to infinity of f of x minus m of x plus c equals 0. Remembering that we can take the mx plus c on the right-hand side and move it to the left-hand side of the equation and include it within the limit because it's still the same thing. Now f of x minus mx plus c is 0 because f of x is mx plus c. Now we'll divide through by x, and of course c over x tends to 0. Take the m to the other side because it's constant, so we can take it out of the limit. And now we have that m, the gradient of the oblique asymptote, the equation, is f of x over x, the limit of that as x tends to infinity or negative infinity. Note that that is not too bad to remember because in fact it is simply y over x. F of x is y. So it's the limit of y over x as x tends to infinity. Then if we go back and we say, well, f of x minus m of x is equal, minus mx is equal to c. Take f of x and subtract mx, we get c. And this tells us that, there we are, there's the c value, the limit as x tends to plus or minus infinity of f of x minus mx. Since mx plus c minus mx equals c. Now remember, this is tertiary. So that's just an explanation. If you understand it, that's good, but you don't have to remember it. Let's do one example using this. I don't suggest you use this method usually in the exam and everything else because these formulae aren't supplied on the information booklet. So you'll need to commit them to memory. And while they're not too bad, y over x, the limit as x tends to infinity, f of x with the mx removed as x tends to infinity. In an exam situation, it's very easy to forget them. But let's have a look at an example. Let's take the limit. Here we are. Here's our equation, x cubed over x squared plus 1. This does have an oblique asymptote because degree 3 for the numerator, degree 2 for the denominator. So what I'm going to do is I'm going to find f of x over x, which simply means multiplying through the denominator by x, finding the limit of that, dividing through by x cubed, and that gives us 1. So there's the value of m, is 1. Now we apply this formula, f of x minus mx, so there we are. There's f of x, and we go to subtract 1x for the formula. Find a common denominator, simplify, and if we divide through by x squared, find the limit as x tends to infinity, we're going to end up with 0. So m is 1, c is 0. So y equals x plus 0. But I emphasize just for information because we're going to use a far simpler method. So let's go back to this, and now we're going to use long division. We're going to divide x squared plus 1 into x cubed. There we are, there's the division. I'm sure you can remember division, and we have a remainder, which means that still needs to be divided. X squared into x cubed goes x, multiply out x squared plus x, subtract, bring down, nothing to bring down, so there's your remainder because x squared won't go to minus x. So therefore the answer to this division is x with minus x over x squared plus 1, it's still to be divided. There it is. So, all we have to do is find the limit of that. Now, as x tends to infinity, the limit of the function as x tends to infinity. That there, we'll do it in the formal way, dividing through by x squared, but you can probably see already that it's going to go towards 0. So here's the limit of f of x as x tends to infinity or negative infinity is x. And there is our oblique asymptote, far simpler. Let's have a look at another one. Yes, oblique asymptote x squared x, so therefore we're going to end up with an oblique asymptote. So let's do the division. X into 2x squared, 2x, multiply out 2x squared plus 2x, subtract 5x, bring down. Now we divide again. X into 5x gives me 5, multiply 5x plus 5, subtract minus 9. No more to bring down. And we cannot divide x plus 1 into minus 9. So that's the remainder. So we're now going to put that back into the equation, which means we have 2x plus 5 and we have minus 9 still to be divided by x plus 1. 2x plus 5 minus 9 still to be divided by x plus 1. There it is. There's our oblique asymptote immediately, 2x plus 5. Because the limit of this is 2x plus 5, because this one as x tends to infinity is going to go towards 0. Therefore the oblique asymptote is y equals 2x plus 5. Let's now sketch a graph with an oblique asymptote. So we must go through all the procedures. So y-intercept, substitute 0 for x, and we get 2. X-intercept, we equate the graph to 0, the equation to 0. Of course, that we can multiply through by it, or just reason that for this to be 0, the denominator must be 0. And we get x equal to negative 1 or 2. Vertical asymptote. Well, that's going to be when x is when x value that makes us undefined, so it's x equals 1. Horizontal asymptotes. They're none. The limit of f of x as x tends to infinity. Remember, that's what we do in order to try to find horizontal asymptotes. Does not exist. Oblique asymptotes. So we get to do our division. There we have it. The equation is y equals x minus 2 over x minus 1. So there is our oblique asymptote, because this is going to go to 0 as x tends to infinity. Y equals x. So, stationary points. Derivative by quotient rule. Simplifying. Put it equal to 0. No zeros. If you substitute the values into quadratic formula, you're going to end up with square root of a negative. Vertical asymptote 1. Oblique asymptote y equals x. I've just drawn the asymptotes as broken lines. Y-intercept of 2, x-intercept minus 1 and 2. Now we need to try to picture here the asymptotes there, so the graph is going to be approaching like that from the outside. And hopefully you could see there's the graph. Another example. Y-intercept 2.5 by substituting 0 in for x. X-intercept negative 2,8, 1,8. Sorry, I'm being very lazy, but you'll be able to do that easily. Equate that to 0, and therefore x squared plus x minus 5 must equal 0, and you have to use quadratic formula. Vertical asymptote, x equals minus 2. No horizontal asymptote, because the limit of that doesn't exist. Oblique asymptote. Right, here we are. We're going to divide. We know it has an oblique asymptote because x squared x, numerator higher degree. So let's do the division, x minus 2 into x squared plus x minus 5. And there we end up with x plus 3, remainder 1, which means y equals x plus 3 plus 1 still to be divided by x minus 2. And there is our oblique asymptote. Stationary points. Phew. Okay, so there's our quotient rule. Equating to 0, we get x equal to 1 or 3 because we need the numerator 0. Y equals 3, 7 by substituting back into the original. Second derivative, and if you substitute x equals 1, we're going to get a negative. And if we substitute 3, we're going to get a positive, which means a local minimum. Sorry, I'm taking you through these graph sketching movements very quickly because we've already done those. So there's our y-intercept, there are x-intercepts, vertical asymptote, oblique asymptote, there it is there. And you'll notice now that these intercepts are on the inside, so therefore we're approaching these asymptotes from the inside of the curve now. There's our turning points, our stationary points, and that gives us an indication immediately of how the graph is going to behave. There we are, it's asymptotic to those lines, so there is our curve.